We're going to start the recording in 3, 2, 1. What's going on, my chemistry students? So we're going to talk about this idea of molarity. And we had a whole discussion about molarity, and we talked about like gross orange juice that my cheap mom used to make, where like she would put the thing called for like 1 can of the orange juice concentrate and then 3 cans of water, whereas my mom would put like 1/3 of a can of orange juice and then like 3 cans of water, or not even that. She would like take a teaspoon out, take that much orange juice concentrate and put it in a can in water. And so what molarity is actually referring to is kind of like the concentration of the different types of stuff that you have. Okay. Now, one of the things that you would measure the concentration in would be something like, all right, 1 second, I forgot to close this other conference completely. One way to measure concentration is you would measure in grams per liter, right? Or maybe kilograms per liter or something like that. No, not kilograms per liter, that probably grams per liter. Okay. But in chemistry, we're not really dealing with grams because different types of solids could have a different, density, and so then your grams wouldn't be measured out, nicely and whatever. So what we like to deal with when we deal with molarity is we talk about moles per liter. And that's really the whole concept behind the last class that we talked about. So Genesis, you're saying you missed last class. This is it. I'm kind of recapping it right now. So let's say that we're going to analyze a alcohol content of wine. Analyze wine. And to do that, we need at least 1.00 liters, so that's my volume, of an aqueous solution of potassium dichromate. And what concentration of potassium dichromate? It's 0.200 molarity. And we just put a capital M of potassium dichromate. So potassium dichromate is CR2O7. Did I make you guys memorize what dichromate is? CR2O7 with a -2 over here. Did I make you guys do that? Yes or no? No? Okay. Anyway, dichromate is CR2O7 with a -2 over here. So potassium dichromate, since potassium only has a +1, you'll need 2 of those to balance out the charges. So potassium dichromate is K2CR2O7. All right, but that actually you didn't need to know. The question is how much solid is weighed out or must be weighed out of this solution. Okay. So if I have, and notice how they said an aqueous solution. So that means a liquid mixture of this stuff. So we usually put AQ on the bottom, and that signifies the state that this thing is in. If it's a solid, if it's a liquid, if it's a gas, we put a G, that kind of stuff. If it's an aqueous solution, which basically means water with ions dissolved into it, we put an AQ. That way, when I write AQ down, you don't freak out. Are we cool? All right. So what we're looking for is how many moles, or what mass of this stuff that we have. What mass of this stuff do we have? All right. First thing I need to do is I need to figure out the molar mass of K2CR2O7. And what I would do is I would actually look that up on my periodic table and calculate that out. Does anyone have a problem with me just writing down the answer, 294.20 grams per mole? Yes or no? I don't know where you got that from. Respond to me, please. All right. Matthew gets understands where I got that from. Genesis is confused as to where I got that from. It's that same old trick that we've been using. You look up the periodic table. You know, I really got to get you guys a periodic table that you guys print up and put on your wall. You look up that periodic table. You look for these small little numbers underneath it. Actually, this one doesn't have a small little numbers underneath it. There we go. Here's the periodic table. The K is 39.0983. So you multiply that by 2 because you have 2 potassiums. And then the CR is 51.996. So you multiply that by 2. And then the O is 16. See that number down there? So then you multiply that by 7, then you add them all up. Yeah. You've played this game. We've done this ad nauseum. So, you know, I'm just going to write that out just to start. Okay. So what they're looking at here is, I would always start with what we're given. We're given 1.00 liters of solution that we need. Okay. And I know that one of the conversions I have is this thing right here. 0.200 moles for every 1 liter. Right? Because the molarity is moles per liter. So it's 0.2 molarity means 0.200 moles for every 1 liter. So I'm going to use that conversion to figure out exactly how many moles of potassium dichromate I have. Got it? And then what I'm going to do is this tells me the number of moles, because the liters of cancels out with that liters. This tells me the number of moles that I have of potassium dichromate that I want. So now all I have to do is figure out how many grams of that stuff I need to measure out. And the number of grams I would do is I would say, all right, well, for every 1 mole of that stuff, I have 294.20 grams of that stuff. And I take this and I multiply 1 times 0.2 times 294.20, and I end up getting 58.8 grams of K2CR2O7. Now, I know that Bradley hates molarity. And I'm wondering, is this hard to you guys? Was that bad or what? Oh, by the way, I'm done. That was my answer. Okay. All right. So, we got to talk about dilution. I'm going to do maybe one. Should I do 1 or 2? Let's just do one more example on dilution. This one's going to be pretty quick. But it's really just the same thing. They make it like it's a separate topic. It really isn't. Dilutions. So in labs, people don't like carrying around like exactly the molarity you want. What they like doing is they like having the super concentrated version, and then they like diluting it down. It's kind of like if you're super like organic, then you probably make orange juice using straight up oranges. Whereas me, Mr. Dalday, I'm poor, so I make orange juice using the orange juice concentrate that you get from the refrigerator section inside of the store. You guys know what I'm talking about? It comes in a little like cardboard tube, and it's orange juice concentrate. And the advantage of that is that I can actually stock my freezer with a lot of that stuff, and I wouldn't need my whole refrigerator full of orange juice if I stocked my freezer with, a few of those cans. You see what I mean? Because I can make lots of orange juice, all I got to do is just, yeah, exactly. I can make a lot of orange juice. All I got to do is just dilute it down. So if we have something like 16 molar sulfuric acid, and I'll be honest with you, that's pretty powerful stuff. 16 molar, that's 16 moles of sulfuric acid per 1 liter of water. That will burn your face off. Okay, I'm not talking about like figuratively. I'm talking literally. And you're asked to find. You want to make. All right, so you have this, and you want to make 1.5 liters of 0.10 molarity H2SO4. So that's hydrogen sulfate. Okay? All right. So let's see. I need to make 1.5 liters of H2SO4. I know that there's a conversion factor right here. How many moles of H2SO4 am I dealing with? Well, I know that for every liter of H2SO4, I have 0.10 moles of H2SO4. Got it? I also know that the other superacid, sulfuric acid that I have, is 16 moles. So I know that there's 16 moles for every 1 liter. So I guess what I got to do is I have to do 16 moles on the bottom of acid for 1 liter. Did everyone understand that last step? Because that's kind of the key. Why did I put the 16 moles of the acid on the bottom? Well, because of the units. This liters over here cancels out with that liters over there. And this mole right here, I wanted to cancel out with this mole over here. Well, I canceled out the liter with the liter over here and here. And then I canceled out the mole with the mole. That's why I put the 16 on the bottom and not the top. Because it's 16 moles of that stuff. That's literally it. That's all you need. So then you take 1.5, multiply that by 0.1, divide that by 16, and you end up getting wait a second, did I do this wrong? Oh, okay. You end up getting 9.4 times 10 to the negative 3 liters, or 9.4 milliliters of solution. So here's what I would do, okay? I take my jar out. I have a jar, and say that this jar is 2 liters. I would take out my 2-liter soda bottle, okay? And then I would fill it up to 1 liter exactly of H2O. Just pure straight up water. And then I would take out 9.4 milliliters and I would put my 9.4 milliliters of my acid, 9.4 milliliters inside. And then so then there's a little bit of acid in there. And then I would fill up the rest of it with water until I reached 1.5 liters. And then I would take a mixing stick and I would stir it up. And that would give me exactly 1.5 liters of a 0.10 molarity concentration of H2SO4. Does that make sense to you? I mean, to be honest with you, I would have actually had you guys make a lab where I'm actually having you make orange juice, but I thought it would be boring. Different concentrations of orange juice. I still think something like that would be kind of cool. But anyway, we got a lot more stuff we got to talk about. And I don't have a whole lot of time. I've got like 15 minutes to introduce you to this kind of stuff. All right. So we're going to talk about different types of reactions. And one of the types of reactions is called chemicals react in different ways. There's one reaction that's called a precipitation reaction. There's one that's called a acid-base. And then there's another one called oxidation reduction. Reaction. And I'll be honest with you, I can't remember completely off the top of my head, but I think this is called a redox. Or at least that's what I called it back in college 10 years ago. It's like an ox redox. That's the abbreviation I did. Although I'm not sure if redox is a different kind of reaction, but I'm pretty sure that that's what it is. Anyway, don't take my word for it. Or at least, hey, Mr. Dalday said that. If your college chemistry professor ends up changing that, then go with what they say. First thing we're going to talk about is the precipitation reaction. Now, what is a precipitation? Precipitation reaction is basically when you have junk inside of your reaction, where what I mean by junk is solids. And you'll see this solid as kind of like a creamy looking substance, or it could actually be literally little sand that forms when you pour two chemicals together. That is where a solid forms as a precipitate. Precipitate. So, a very common one is potassium chromate. So it's K2CrO4 in an aqueous solution. And if I combine that with, I think it was barium nitrate, so that would be BaNO3, aqueous solution. Let's see if I can look it up online and see if I can find a nice picture of that. Let's see. Come on, internet. Go, go, go. All right, so let's see. Potassium chromate and barium nitrate. All right, there we go. So when I mix potassium chromate, here's potassium chromate. No, wait. This is potassium chromate, I think. And this is barium nitrate. And when I pour one into the other, what ends up coming out looks like this. Got it? And you guys see that cloudy crud that's in there? That's a solid forming. In fact, it kind of looks like that, which is pretty gross. But, you can see these reactions. And if I were to dissolve that, it would give me this. Now, the question is, what is this? Is this barium nitrate? Is this potassium chromate? Or is it a combination like barium chromate or potassium nitrate? And, okay, here's a nice picture. This plus that gives me that. And you can see the crud that forms on the bottom. So what we do is we actually go through it and we try to figure it out. So let's see. I know that if I add K2CrO4 and I add that, it will give me products. So this is the normal equation that I have you look at. And then what I do is this is the normal equation I have you look at. This is only the left-hand side. When I'm putting these when it means it's in an aqueous solution, this means that this thing is actually broken up into its ions. So let's break these up into its ions. Potassium ion is K+. Got it? And I put an AQ for standing for aqueous. And there's 2 of them, so I'll put a 2 out there. The chromium ion is CrO4 with a 2-. And there's only one of those. Aqueous solution. And then the barium ion is Ba2+, aqueous solution. And the nitrate is NO3, but since there's 2 of them, I'm going to put a 2 out in front of there. And it's just a minus for aqueous. And you can see why I have a 2 out here, because there's 2 potassium, the positive ones, combined with one of these -2 ones, so that it balances out and makes that thing right there. And then the barium does a similar thing. Questions, comments, concerns, vomits, etc.? Okay, so here's what I can do. From these ions, my solid could be a few different things. That solid that comes out could be potassium chromate, right? Because it's 1 cation and 1 anion. It could be potassium nitrate, and I would only need 1 potassium and 1 nitrate. It could be a barium CrO4, could be a barium chromate, and it could also be a barium nitrate, Ba2, NO3 minus, or NO3. Do you guys understand what I did here, where I got these 4 options from? All I did was I combined them. I said it could be this and this, it could be this and this, it could be this and this. Actually, it can't be the second one, because I have to combine the positive with the negative. Can you guys hear my voice? Do you guys understand me? I'm just making sure you guys are all on the same page here. Yes, no? Okay, all right. Do you guys understand where I got my 4 options from? Okay, good. What I'm going to do is I'm going to rule out this one and this one. No, wait. That one and this one. And the reason for that is because of this. It's very simple. If I look back at my picture, one of these solutions was potassium chromate, and one of these solutions was barium nitrate. And in either of these, I didn't see any solids. Do you guys see what I mean? So how could my solid be made up of potassium chromate when the original aqueous solution was potassium chromate and it didn't have a solid in it? And the original solution of barium nitrate I put in didn't have a solid in it, so I'm guessing that solid aren't these 2 things, because that's what originally came in. So it's one of those 2. Now, the the question is, which solid does it? Is it barium chromate or is it potassium nitrate? And the answer is, if you know what potassium is, I guess potassium and nitrate solutions are both colorless. So if there was a solid to be formed, it would be a white solid. And obviously, this is not a white solid. You guys see what I mean? So, based off of that knowledge, you would be able to say, well, then the stuff that we have must be barium chromate. And the overall reaction that you would get is you would have, all right, I would say K2Cr04 aqueous solution plus barium nitrate. I'm going to write down my reaction now. NO3 with a 2 there, aqueous solution, will yield barium chromate. And instead of an AQ, I'm going to put a solid there because it's a solid precipitate that got formed. And then the KNO3, that's the other one. But in order to balance equations, I think I need a 2 here. Is that correct? Let's see. There's 2 potassiums on this side, I have 2 on this side. There's 2 NO3s on this side, I have 2 on this side. There's 1 barium on each side, and there's 1 chromate on each side. So it looks like this equation is balanced as well. Are we cool with that? All right. One way to write this is, actually, we don't go into talking about the different ionic equations. I'll tell you what, we have 5 minutes. Let me show you one more, and then I'm going to introduce you to, actually, you know what? I'm going to introduce you to the table, and then we'll go over this example problem over here. Let's see. Let's download it. Let's see. In your textbook, you have, do I have your textbook on this computer? No, I don't. All right, let me pull up your textbook. In your textbook, you have a table. It's table 4.1 on page 156. Write that down. Because some people would ask me, well, how do you know these rules as far as like, how did you know that the potassium chromate or potassium nitrate was actually a clear solution, and then the thing that would have formed would be potassium chromate or barium chromate? And my answer would be is we came up with these rules for chemistry. And it's just this table. And the table, the book actually tells you memorize this table. I say don't memorize the table. Yes, it would be very advantageous if you memorize the table, but I don't care if you don't memorize the table. Look up the rules if you guys ever need them. Okay? I just think it's too much to ask you to memorize this table. But here it is. You guys see these rules? Let's go over a few of these example problems and we'll use these rules. So, simple rules for solubility in salts in water. Most nitrates are soluble. So what forms an aqueous solution? Most nitrates. Most salts containing alkali metals, so potassium whatever, is usually going to form a solution. It's going to break down into its ions when you put it in water. Most chloride, bromide, and iodide salts are soluble. Notable exceptions to salts containing those ions are salts containing the ions with silver, lead, or mercury. Most sulfates are soluble. Notable exceptions are barium sulfate. So if you have an SO4 deal, it's soluble except for barium sulfate, lead sulfate, and mercury sulfate, and also calcium sulfate. Most hydroxides are only slightly soluble, which basically means they're not very soluble at all. An important soluble hydroxide is NaOH, so it's a soluble hydroxide, and KOH, which is potassium hydroxide. The compound BaSH, or barium hydroxide, strontium hydroxide, and calcium hydroxide are marginally soluble. And read the text to figure out what these words kind of mean when they say slightly soluble versus marginally soluble and that kind of stuff. Most sulfides, carbonates, chromates, and phosphates salts are only slightly soluble, except for these ones containing certain cations in this rule up above. All right, let's talk about what the heck I just said. Okay, it's actually pretty straightforward. Let's do some of these examples. Potassium nitrate is going to be added to barium chlorate. Okay? Potassium nitrate, barium chlorate. So here's what we want to do. Potassium nitrate in water will make these ions break down. All right. Is anyone curious as to know? Oh, actually, you know what? I didn't even cover that. All right. So the reason why I know that this thing breaks down as an ion is because if you look at Rule 1 and Rule 2, you can see that potassium, something with this metal ion, it's an alkaline metal ion, and also it's a nitrate, so obviously it's going to break down. Barium chloride is also going to break down in the solution. So because, let's see, why did I say that? Well, because most chloride, bromide, and iodide salts are soluble. So rule number 3 tells me that that's going to break down as well. So what's going to happen is, what are some possible solids that could be made? Well, if you take these two solutions and you mix them together, you could have potassium chlorate, or you could have barium nitrate. Got it? And actually, potassium chlorate will dissolve in water because, according to the rules, anything potassium dissolves in water. And also, barium nitrate dissolves in water. So actually, no reaction is going to occur. If you take potassium nitrate and barium chlorate. Because everything gets dissolved. Maybe that wasn't as good of an example as I wanted to. Let's try this one. Sodium Na2SO4, sodium sulfate in an aqueous solution gets added to lead NO3 2. All right. So I know that the sodium sulfate is going to break down. There's going to be 2 NAs, and there's going to be an SO4 with a 2 minus. There's also going to be 1 lead, and a NO3, but there's 2 of them with a minus. Do you guys understand how I got from here to here? Yes or no? I looked at my rules. My rules are right here on the left-hand side. The sulfates are most sulfates are soluble, except barium, lead, and mercury. And apparently, I have a sodium sulfate, so that means that thing will break down into its ions, according to these rules. You can see in rule number 4. Over here is most nitrates are soluble, so my nitrates will break down. So my left-hand side of my equation is going to be something like this. You guys got it? Now, what kinds of solids could be formed? Well, I already have an NaSO4, so that obviously isn't the solid that's formed. So it must have been like an NaNO3. NaNO3. And this has a minus on it, and this has a plus on it, so I don't need to add any coefficients or double these compounds in any way, because the 1 plus balances out with the 1 minus. Also, another solid that could be formed would be the PbSO4, right? Now, what is the NaNO3 going to do in water? It's going to break down into its ions, right? But what is the PbSO4 going to do? Well, most sulfate salts are soluble, except BaSO4, PbSO4, Hg2SO4. This is a PbSO4. So apparently, if I combine sodium sulfate with lead nitrate, it's going to form a lead sulfate solid. And let's see if I can find a picture of that. Sodium nitrate with lead sulfate. Sodium nitrate and lead sulfate. Wait, is it sodium? Oh, sodium sulfate. And lead nitrate. Okay, and if you can see in this picture, I don't really have good pictures. Oh, there we go. This is the solid that forms, I think. I wish I had these chemicals on me so I can actually show you what the solids look like, but anyway. I apologize, I don't have the chemicals on me. Cool? All right. I'll be honest with you, the best way to learn this last part is to know that you have a table available to you. Am I going to ask you to memorize it? No. If I ask you to do this on a test, I would give you the table. Will your college teacher ask you to memorize it? Probably. But will Mr. Dalday ask you? No. I'm not a big memorization person. But I do want you to be able to go to the correct spot and look it up. Like, for example, Genesis, I was a little disappointed that you didn't know where I got that 294 point whatever from, because even though you don't memorize all of the molecular masses on the periodic table, I'm not going to make you do that. I do want you to know that you can go to a periodic table and look all that information up. You see what I mean? So I want you to at least have this available to you so you can print it up and put it on your wall or something like that. Yeah, don't worry about it. I'm not really disappointed. I'm just, I was kind of surprised that you didn't know that. Anyway, I'm going to go. I'll talk to you later. All right. Okay, bye.